All right, I guess it's time to kick it off. As mentioned, good morning, good noon, good afternoon, depending on where you're joining from. We are actually joining today from San Francisco here. So for us, it's still like rather early morning. And us, that's me, that's Jörg. So I am if my slides would move, yes. I'm the head of engineering and head of machine learning infrastructure over at ArangoDB. Before that, I built a lot of infrastructure stuff around Kubernetes, Mesos. I dealt a lot with different distributed database systems during my PhD. So kind of this intersection is actually something I'm very passionate about. And this is also why we're going to talk a little bit about distributed graphs later in this talk. I unfortunately, let's just say I'm mostly focused on the books around Games of Thrones. This is why I got Gudrun here. And Gudrun is just the expert for both.
Hi, everyone. So the reason I'm on, usually I'm the talent acquisition manager at ArangoDB. Today, I'm on because I read all the books twice. So once in German, my native language, and also in English. I watched the series, and I also have opinions about Game of Thrones. So I guess a lot of people out there, we do not want to start a discussion. But yes, so especially after the last season and the season finale, I guess a lot of people have opinions.
How much are you going to spoil?
No, I'm not trying to spoil. So,
okay.
I mean, we just voted, or in the chat, I saw some people haven't actually seen all the seasons and haven't actually seen the last season yet. So I try not to spoil. So.
I think we have some small spoilers. So if you really don't want any spoilers, probably this is the wrong webinar for you. But still, I guess we got more spoilers about graph and graph databases, and we have deep spoilers about Games of Thrones.
One thing perhaps I want to I want to show you guys. So actually I started reading the books already in the 90s, and I went actually to my parents' home, and I found the book with this can you see this? Very ranchy kind of picture on top. And I kind of wondered why my parents actually let me read something like that, but yeah.
Are they watching this series?
No, they have no idea. So
cool. So what are we actually talking about today? As the title suggests, there are two parts to this webinar, or kind of like it's intermingled. So on the one hand, we're going to talk about graphs, and we're also going to talk about Games of Thrones. And the idea for this webinar actually came from, we were kind of discussing about Game of Thrones. I was like, I actually don't know too much. And then when talking about it, we figured out that actually a lot of that can explain through graph structures. And a lot of the knowledge is actually embedded in graphs. So I feel this is also a very good webinar to just figure out how to actually approach certain problems from like a graph perspective using Games of Thrones. So what is a graph? Let's start with like the first part of the title. So a graph basically consists of vertices and edges. So here, for example, we have just a simple social network, or like a relationship between people. So there are certain people like Alice, Bob, Charlie, and Diana, and they have relationships in between them. So for example, Alice is married to Bob. Bob is a friend of Diana. And as here right now, those graphs are actually unidirectional. This currently would only go in one direction. But there are also graphs where, for example, Mary typically is like a symmetrical relationship. So if Alice is married to Bob, Bob typically is also married to Alice, at least in most jurisdictions I know. But this is kind of like what a graph is about. And now we can basically have queries around that graph, like who are all the friends of Alice's husband, or similar queries. And we're going to see a bunch of them throughout the webinar. Why actually ArangoDB? So why came that up? Why are we doing this from ArangoDB? So there's actually more to graphs than just the graph itself. Typically, like the example we saw, it's a very basic example. In real-world scenarios, we typically end up with a mix of different data types. So for example, if I just switch back here, this would work well if it's really only like the names of those people we would care about. But typically, there are actually larger documents attached to that and more meta information. So for example, Alice probably has a social security number. Depending on which country she lives in, she might have a passport. In Germany, we got like so Steuer IDs and a lot of different metadata. And this metadata can actually vary between people. And this is why having a way to store it, the internet is kind of slow, so I'm jumping. So basically having something where I can have a very flexible schema to store this kind of like unstructured information, like a document or JSON, is super useful. But then on the other hand, we got those connections in between them. As we saw, they have like relationships to each other, like they are married, they are friends, or other relationships. One might work for another person, so there's a boss relationship. And so on and so on. And this is why typically in real world use cases, we not only end up with a graph use case, but we actually end up with a mix of kind of different data types. And we're going to see that ArangoDB is actually very well suited for that because it's a native multi-model database. So basically at its core, it's not having a single like database kernel to do all the graph processing, another kernel to do like the document style processing. It's being all done from like one database kernel. And by that, we kind of have the speed. We don't have to switch between different database kernels. And on the other hand, we can actually also have transactional guarantees across that. All right. And that brings us actually to the second part of the title, and that's graphs of Games of Thrones. And therefore, I would actually hand over to the expert here next to me.
So basically, Game of Thrones is a perfect example for having very complex relationships. I saw before some of you actually have never read it or neither watched the TV series. So I perhaps just give you a quick introduction. The original series, it started as a book series, and it's located in Westeros, and it basically revolves around the phase of the 9 great houses of Westeros. So we have 9 great houses consisting of Stark, Baratheon, Tully, Greyjoy, Lannister, Tyrell, Martell, and Targaryen. And what's especially interesting about the books is that the relationships are kind of very complex, very layered, to be honest. It's not always clear how the relationships actually started, where they are. And as you see perhaps in this picture, which is a perfect example just of 5 people, we have, for example, we have love, we have loyalty, we have marriage, we have death, we have violence, we have sex. So basically, everything which can happen between people will definitely also happen between the death of the characters in Game of Thrones.
That was actually one of the hardest things for me in the beginning, to just figure out like who is who and who's related to who and who's going to kill whom and so on and so on.
Yeah, I mean, basically in the books we have, I think, about 2,500 characters, and they broke it down in the series to about, I think, 500 cast and 100 main characters, kind of, but it's still very, very complex to follow.
Where does the title come from?
Game of Thrones, basically, the title is coming from that the whole Westeros is united under the king of Westeros, which is sitting on the Iron Throne, and every family tries to, of course, through allies, through schema, through violence, through battles, try, of course, to sit on the Iron Throne, or at least have someone in their favor on this throne.
To rule
them all.
One to rule them all. That's a different webinar.
Yes.
All right. So what has that to do actually with graph structures? So graph structures, as we already figured out on the previous slides, it can be super helpful to model a lot of things like relationship. Who's related to who? Who is killed by whom? Which from what I recall, there are a lot of people dying throughout the book. So it's actually pretty hard to keep track of who's killing whom and who got killed by whom in the end. And also, especially as that is changing over time, it's also about like alliances or battles between different houses. So who was fighting with whom, who was ally of whom, at which part of the series, and so on and so on. And another actually a very interesting aspect, which can also be modeled very nicely, is just kind of locations. We probably don't have enough time in this webinar to go like too deep into that, but just also ArangoDB is supporting like geospatial queries. So we could, for example, figure out which character has traveled the most distance across all scenes, or just kind of queries like that. Because it's actually also a graph problem, right? You're moving from point A to point B. You can have proximity queries like what are the characters next to each other, what are the houses, what are the castles next to each other, who was killed in this castle, and so on and so on. So there's actually a lot we can represent as a graph, and we'll see some examples immediately right now if we talk about relationships. Relationships are actually not always obvious in Games of Thrones. So just simple questions like, who are Joffrey's parents? Do you briefly want to explain who Joffrey is for those people who actually haven't watched that?
He's one of the persons I think everybody has an opinion about. He's already introduced in the first series, or also in the first book. So he's one of the main characters. Basically, he is the son of the king in the beginning, but very soon everybody's going to find out that his father. Am I going to allowed to say that? Yes.
That is a bit more complex. Yeah.
It's a bit more complex.
Other questions are just like, if we just want to see like ancestry, I mean, this is a lot about family heritage. So if we just want to figure out who are all the ancestors, for example, of Bran, who are the bastards? So basically, who was not born out of a marriage, but the father or mother might have figured out some other partner. And also a reoccurring theme is actually incest here. Is also all royal families. So they sometimes prefer to stick to themselves. So those are actually all queries we can answer from like a graph perspective. And let's actually just jump over to ArangoDB and see examples of that. So here, if it's loading. All right. Let's see which one is passed. Let's log into the new one. So here, this is basically our ArangoDB UI. What I did here, I simply started a Docker container on my local node. But as mentioned, like typical production scenarios, it's more going to be like a large distributed cluster. And what I did before the webinar, I actually just imported all those data sets here. And the two parts here where we're going to be interested in are the characters, which is kind of the document description of the characters, and the relationships between them. So you can already see there are kind of different symbols for them. And one is called like a normal collection, which is just a collection of documents describing the characters. Like very simple here. So the key is just, in our case, a name, and then we got like some more information about them. And the other is actually the relationship between them. So we see it's kind of like, you can imagine it being like an arc in a graph, going from like the character, for example here, Bran Stark, the relation to Ed Stark, and the relation is Ed is Bran's father. So those are the kind of like different relations, and this is kind of like the join in between. And now we can actually have a lot of queries using that. So I prepared some because I didn't dare to type them live during a webinar. And by the way, this is also all open source. So if you want to run that after the webinar, feel free to just do so. So here our first question is actually just who are Joffrey's parents? So if I run that, we see here actually 3 parents, which typically is surprising, right? And I guess this kind of goes in that same direction you were hinting to before.
Yes. So I mean, the show and also the books are not shying away from very difficult topics. So basically, Cersei and Jaime are brother and sister. And they have kind of a love child, which actually, of course, the king thinks is his real son. But yeah, so some people have to die because they found out this very
the truth here.
Yes, incestuous relationship. And yeah.
So this is why we already have like here, down here, we can see like Robert kind of believes he is his father.
Yes.
I'm not sure he actually believes that, but yeah, at least to the outside.
Yes.
And then Jamie kind of also is his father, probably the real biological father in here. All right, let's move over to another query, and let's figure out like who are Brand's ancestors. And then we can actually also figure out what's the difference between those queries. So that was a pretty simple query. So here we actually get more complex, but let me just run it first. So we kind of see all the ancestors, and we're going to look at the ancestor level in just a second. But first, let's actually look at the query, what we are doing. So we are querying our characters edge collection. This is this collection like with the arcs in between different people. And we're starting with the node Bran Stark, because we want to know who is the ancestors of Bran. And then to just understand what's going on up front here, let's start from the beginning. Like each of those graphs can actually have a different part. So ancestor, this is pretty much just the keys. This is the document we saw in the other relation from where the arc is starting or where the arc is ending to. Then we have the edge, which is kind of the connection in between, because a connection can actually also have different properties. So for example, in the previous query, we checked like, is it father, is it mother? This is actually a property of that edge in between them. And then here, so we're actually going multiple levels up. So we're actually not only checking like his direct parents, but we're also checking grandparents, great-grandparents, and so on. We also can look at the past. So basically, how did someone get up to that past? Maybe we can actually just return that past in a second so we can see what that means. But first, here's this 1 to 4. This basically means like how many steps do we want to make in that graph. So here we actually want to see all ancestors from his direct parents, so a distance of 1 in the graph to a distance of 4 in the graph, which should be his great-grandparents, right? I hope I got the correct number of grand here. And to kind of just measure that, we're actually returning the length of a path. So what does that mean? We're actually checking like how many steps is that ancestor away from Bran itself. So Ed, we can see here is like 1 hop away because he is his father. Then we have Richard, who is 2 steps away. So he is his great grandfather. He's his grandfather. Yes. And so this is why we're here 2 away. So kind of this is the length. If we also just want to see like the direct relationships here, we can modify the query a bit. As mentioned, we can do some stuff live. So, and I hope this is correct. So here, now we can actually look at the direct path, how we got here. So for example, Ed Stark, it's the edge going from Bran directly to Ed, and the relationship is father. This is why we had like a distance of 1 here. And then Richard Stark being the grandfather, there are actually 2 edges in the past. So past is kind of like, how can we get from Bran over to Richard? And the first step on this path is we're going from Bran over to Ed, and then we're actually going from Ed to Richard. And both is of relationship father. So this is kind of how we can explore that graph and kind of like figure out all the entire heritage structure here. All right, let's actually go to the next query, which becomes a bit more interesting. So we are trying to investigate this incest habit in Westeros here. And so for that, what is kind of the graph query we want to figure out? We want to find characters whose parents again have a joint parent. So where father and mother actually end up having same parent, at least one of them. And what is an easy way of kind of doing that? So for that, for each person, we kind of just get the grandparents, so the set of all grandparents. And this is actually what this subquery here is doing. So grandparents, so for all ancestors of that character, we're just going like we're not checking the first hop, so we're not interested in like father or mother. We're really only caring about any nodes which are like 2 steps away. And for those, we just return the name. So basically, this is a set of the all grandparents. And then an easy way to just kind of like filter out whether this is unique or not. So basically, are there duplicates in there? We just kind of count how many grandparents there are. And then we actually check how many are distinct. And if this is different, this means some grandparent actually ended up in there at least twice. I cannot imagine like more than twice, but yeah. And so in that case, so we basically filter only those ones where those counts are different, and then we return the character key. So if we run that now, here, we actually see all like Joffrey. We already discussed. This is because Jamie and his sister had a lovely relationship. But interestingly, we also see Jon Snow here. And I guess this is where we get into spoilers, or?
A little bit. So people who do not want to know the face of Jon Snow, no, do not listen, please. No, basically, I mean, Jon Snow is introduced as a bastard child of Ned Stark, and some unknown woman he apparently got pregnant while being in King's Landing. Later on, the story changes a bit. So basically, Ned Stark is not the father of Jon Snow, but he is the uncle. So there was a secret relationship between Rhaegar Targaryen and Ned's sister. And they actually had a child, which is Jon Snow, which survived and which Ned more or less took under his wings since he saw it as his own blood. I mean, this is always what he said, like, he is my blood, don't ask any questions. And now we know kind of why.
So to actually see that in more detail, again, this pass variable we talked about earlier can be super helpful. So if we look down here, I move that up, not as much as I would like right now. Yes, this is better. So let's actually figure out where's kind of the duplicate. And if we scroll through, we easily kind of see it's actually Richard Stark here, which is a grandparent, and he actually comes up here again. So to just figure out like why is he in there twice, because Jon is not like a real incest child, right? So this is actually, let's figure out the first pass here. So the first pass is Lyanna, who's his real mother, right?
Exactly.
Of Jon Snow. So there's a relationship mother, and then Richard is actually the father of his real mother. And then the other part to this, where he comes up again, is down here. So let us check out how we get again back to Richard. So Ed Stark is the pretended father of Jon, which everyone believes in the beginning. And then actually Richard again is the father to Ed. So this is why our query would actually return Jon. And I feel for me, this is just kind of like one of those aspects where we actually have to be careful when doing graph queries. We often make a lot of assumptions about how many parents there are, for example. And we should just be aware that there might be corner cases like this one, where we actually should distinguish, is it a biological father, or is it kind of like a pretended kind of father? Something similar might have happened, for example, also in like Joffrey's case. So where it's kind of like more complex, the assumption might have been that they're always like just 2 edges, like one father and one mother from a person. But as we see in this case, this is not always true. All right. I guess this is enough about relationships. And next, let's actually talk about battles. This is, I suppose this is why you enjoy watching the series, right?
Yes, a bit. So, I mean, they really, honestly, they really do a great job in showing the battles. So that's definitely my opinion.
So here, for example, we can ask questions like, in which battles did the Night Watch fight? Who attacked the Night Watch? Who fought alongside the Night Watch to kind of like figure out alliances? And also like an interesting query probably is like whose alliances changed over time. So where there kind of like houses which once collaborated, and then they actually figured out, let's fight each other and attack each other. And one interesting aspect, as mentioned, we wanted to talk a little bit about how we can think about graph structures. And for that, I just would like to show you the data set being used here. So it's Kaggle. So if you're like into machine learning, they have like a really cool like machine learning contest where you can predict stuff. And in this case, it's actually, this data set is about predicting who might die in the future based on content. And if we look at our battle CSV data set we're using here, this kind of looks like that. We got a total of 25 columns here. We got a name of the battle. We got a year. Every battle has a number. There's attacker, defender, king. There are a bunch of attackers. So you can already see this is kind of like forced into like this relational format, because we got like attacker 1, attacker 2, attacker 4. What happens if there are more than 4 attackers? There are defenders. Again, also just going up to 4. So what would happen if there are more people collaborating or more people defending? We got an outcome, battle type, how many people have died, how many people attacked, and just all that kind of stuff. So this is kind of the original data set. And if we look at that, how can we actually force that into a graph structure? So in a graph structure, we're going to have more individual entities. And so, for example, we have an entity like this document battles. This battle document might have certain fields. So, for example, the year, which belongs to a battle, the number of people participated, the number of attackers, the number of defenders, the outcome of that attack. So this might all be metadata towards a battle. And then this relationship we saw before, we got like attacker 1 or defender 1, attacker 2, defender 2. This we can actually model through a graph edge. So we basically just keep track of all persons in a different collection. And then all of this can actually just be modeled by an edge between them. So in a battle, some person was an attacker in this battle, another person was a defender in this battle. And here, this is actually just modeled as a graph edge. Similarly with locations, battles have like a certain location. So, and each of those locations might be in a region. You can already see like several advantages. So first of all, we don't have to duplicate like all that. We don't have to write person in every line and kind of like duplicate all the metadata. Similar with locations, we kind of only have to store that edge in between them. And especially if you imagine that we have a lot of metadata about a certain location, so we have a lot of metadata, so the document for a particular person is pretty large, this actually saves a lot of time. If you recall, or if you ever had to take database classes during university, college, or your free time, if you like that, you might remember different normal forms. And so for me, this actually reminded me a lot about breaking like a big relation down into like different normal forms, like up to third normal form, Boyce-Codd normal form, because we actually try to put out duplicated parts in between different in between like one big row of the relation, and kind of just puts that in different relations. So we split it up into a battle relation, into a person relation, location relation, or region. So if you actually have a relational database structure, which is in like third normal form or something even higher, putting it into a graph view is pretty straightforward. All right, this actually leads us to the queries we want to ask about the battles, right? So let's switch back to ArangoDB. And we got like here some more. So we got like, this is pretty much the same representation we saw earlier. So we got the attacker edge, which is connecting battles to the persons who were attacking in this battle. And similarly, we got a defender edge back here. We got the different houses. So basically like which house was an attacker, which house was a defender. We got the locations. So basically all those entities we just saw earlier. Let me briefly switch back to my queries, and let's actually ask the first query, and who attacked the Night Watch? or in which battles the Night Watch was actually a defender. So what we do for that, we actually loop over all houses, because we might also just do the query for all houses, but we filter because we're only interested in Night Watch here. And then actually we check for kind of like all those edges in defender edge. So basically everywhere where Night Watch used to be defender, we return the battle name. So we kind of use this defender edge to kind of make that connection back to the battle and see in which battles they were active. And here they were defending in the Battle of Castle Black.
Yeah.
What happened there?
Basically, we haven't introduced properly the Night Watch yet, so perhaps we start with that. I just talked about the different houses. So actually, we also have, in the north, we have a very unknown dark force, which is attacking or has attacked in the past during the long winter, which turned out to be kind of ice zombies, so the White Walkers. And basically the Night Watch is the defenders, which are consistent of people of different houses. So this is also interesting for the query, that defend against these White Walkers whenever winter is returning.
So but it's a common thread for all the houses.
Definitely, yes. But in this case, there are also wildlings still living behind the Great Wall. So basically, a Great Wall was built to keep the White Walkers in their place. There are still wildlings and other giants, creatures, whatever you want to call it, still living behind this wall, and they are now pushed more or less against a Castle Black. So,
all right,
it's an epic. So,
as we already figured out, and as we're now talking about those creatures, so we talked about this battle here. Let's actually figure out who attacked the Night Watch there. So for that, we actually if you remember, before, the query pretty much went to here, and then we just kind of returned the battle name. But now we actually continue. So for each of those battles, we kind of figure out who are the attackers. So for that, we can use the attacker edge going out from this battle instance and just figure out who was the attacking house here. So if we run that, or the attacking party, we get the Free Folk, Sands, and Giants.
Giants, yes.
Giants.
So in this particular battle, they are more or less pushed towards the Great Wall by the White Walkers and attack the Night Watch more or less, kind of to defend themselves, to get past the Great Wall. So so everybody kind of attacks the Night Watch in this case.
not everyone, right? Let's actually see who fought alongside the Night Watch. And again, it's pretty similar up to here. So we identified the battles they have fought in, and we're going to see this in just the next query. This actually also works for more cases. But now we actually check the defender edge. So we want to see who was the other defenders in that battle. As we already know, Night Watch is one of them. We just want to filter that out. And then we just return that as the allies who helped the Night Watch in this case. So if I run that query, we get the Beressians.
That's very interesting, to be honest.
Okay.
Beressian, I think basically Beressian is coming up because at that time of the battle, Beressian was still holding the king, the throne, I think. So okay. This is at least what I would assume from this query.
All right. Yeah. Okay.
So basically, I mean, the king supported since I mean the original King Beressian died, so perhaps I can spoiler that. And since Joffrey technically is not his son, but has a Beressian name, was in this case, I guess, on the side of the Night Watch.
All right. What we have done so far, I mean, the Night Watch, they're probably more interesting people who fought in more battles. And for that, we now actually want to check not only defending, so the Night Watch, we only checked here in which battles they have been defending, but let's actually figure out in which wars the Lannister have fought, both on the defending side and also on the attacking side. and who were kind of their allies in that. So what we can do for that, we just kind of have two subqueries, which are pretty similar to what we saw before. So we again, here we just figure out who are all the allies where they defended. So this is pretty much the same we saw earlier, but now we actually have the same query for in cases where they are attacking. And then we just form a union across that, and then we return all the allies here for whoever have fought alongside Lannisters. And then we get House Frey and House Bracken.
Okay, interesting. So Freys basically, I mean, they switched sides at some point. So basically in the start, they were more on the Stark side. But for everybody who remembers the Red Wedding, they switched sides to the Lannisters at some point in a very epic chapter.
All right, so you're saying if we look at now the enemies, so who is kind of attacking, we should see them again, not in this data set, but that might actually be this data set. So this is just a crawled data set. If you want, it's actually all the credits to the people who crawled that are in the slides, which we're going to share later. But here we basically see the opponents who have fought against the Lannisters. It's actually a bigger set, right? So seemingly they're not too popular.
Yes. So yes, definitely. So Lannisters are not the most popular house in the world, but they have money. So I guess a lot of jealousy also, but I mean, they are also kind of bastards in the literal term.
So, and again, this is super similar to what we saw before. It's basically just, instead of like attackers, we kind of check the opposite. So in cases where the Lannisters were defending, we are interested in the attackers in those battles. And in the battles where the Lannisters were attackers, we're interested in the defenders who were attacked by the Lannisters here. All right, this actually now hopefully gave us like some kind of idea how we can model problems in terms of like graph trees. And let's actually talk about how we can scale those. So if we have a lot of relationships, imagine like for each scene in the series, for each scene in the book, we want to store all this information. This might actually not fit on like a single node. So also if you come up with other real life graphs, they can actually become rather big. And so what ArangoDB actually supports is splitting a graph across multiple nodes, which works really well. You just add more DB servers. You can also add more coordinators. So if you want to imagine that DB servers, they're kind of like in charge of data, and the coordinators are just in charge of kind of like routing the query and receiving the query from the other side. So just kind of like the, coordinating the query here. But a challenge we are having here actually is that we have graph edges which go between DB servers. So for example, in between here, here's an edge where a node on DB server 1 is connected to a node on DB server 2. Here again, and similar with DB server 2 and DB server 3. And if you remember the latency numbers every programmer should know, otherwise, there's a really cool website, I think it's by Berkeley, but again, it's in the notes for the slide if you want to check it out later. The cost of actually like a main memory reference is around 100 nanoseconds. When we're talking about a round trip, which is kind of like the minimal thing we have to do if we have to like go over to that other node, request the data, and then go back, we are at a totally different range. So we are talking about like 500,000 nanoseconds here. So this is probably something we should avoid, and it can easily impact performance. And this is actually why ArangoDB implemented like a smart graph feature. So that smart graph feature is actually figuring out over time how many edges are kind of going between nodes. And then it tries to reshuffle data. So if we look here, so for example, it tries to move nodes that we actually minimize the between node communication. So in this case, we could actually just move this node over here. We'll move this node over to DB server 2, and so on and so on. So we actually end up with a graph where we have way less between node communication. So we're saving a lot of time and we get a lot of performance out of that. So this is kind of like an optimization for distributed graphs, which just makes it run performant. But also, if we're dealing with larger data sizes, we should talk about how we can scale those different collections. So what we saw earlier, we already had a collection for different persons in Games of Thrones. We had a collection for different locations. So each of them is describing like certain metadata about the person, about the locations. But actually, even in the books, you mentioned how many different persons were there?
2,503, I think.
Wow, well, that's pretty precise. So, but even that, this is actually not that much in terms of what can be handled on a single node. So the challenge here is, for example, like here, all those persons, they are lying like on a single node. All the locations, again, this is fitting on a single node, can fit here on DB server 2. But then we get the different scenes. So there are a lot of scenes in both in the series as well as the books. So actually, this probably wouldn't fit all on a single node. So we actually have to chart that across different nodes. So we got like scenes here on DB server 1. We got another subset of scenes on DB server 2, and yet another like on DB server 3 over here. And then the coordinators, as mentioned, like if we send a query, they're actually in charge of querying all of them in parallel. But if we actually need other information, if we're joining, for example, with location information, so there's an edge in that graph going from like scenes to locations, similarly like from scenes to persons, this actually means, again, we have to shift a lot of data because each time we're doing something with scenes 2, we need certain metadata from persons, which is a collection lying on DB server 1 over here. And similarly with locations, and here the search charts, that's actually particularly bad because it needs to get like all metadata from either DB server 1 or DB server 2. So how can we actually scale those collections? And this is where we get into satellite collections. And I hope it's going to move. Yes. And the idea about satellite collections, it's also, if you've ever worked with MapReduce or something like that, it's called replicated join. We can actually replicate smaller collections across all nodes. So as mentioned, persons, even though if it's like 2,000 persons, this is still pretty manageable. This is going to be like in a small megabyte range at most. So putting this person collection on each of the nodes is actually not that costly. Similarly with locations, again, I seriously doubt, I'm not sure how much metadata we have, but if that's more than 100 megabyte, I would be super surprised. No. So we can actually, again, just replicate that across all here, across all nodes. And now, if we're actually sending a query, each of those joins, each of the metadata from the other charts, from the other collections, can be retrieved locally on the node. So we don't have those ugly red edges between nodes and much less between node communication. So those are all kind of like tricks and performance optimizations to really make those graph and document queries at large scale. And it's really interesting patterns overall in database systems, how we can scale, especially those connected data sets. You've seen we need to kind of reduce the between node communication, and we've seen like two potential ways of doing that, either by moving data in a favorable fashion, that it's staying like on one node and we can do most of the queries locally, or actually replicating smaller data sets between multiple servers, and by that actually having the data available locally as well. All right, that was our short insight into graphs. We'll probably do a follow-up webinar with like more advanced techniques. Feel free to suggest a topic if you want to dive deeper into Games of Thrones, if you want to learn about Lord of the Rings or whatever.
Avengers.
Avengers, yeah, that's pretty good. Again, I really haven't watched that too much, but yeah, that's why you're here. And otherwise, feel free to ask questions. or just ping us. Are there any questions? Let's check.
So one question is, will a recording be available? Yes.
The recording will be made available, yes. And as mentioned, like the slides will also be made available. The next question here is, what is performance benchmark? There are different performance benchmarks. And with benchmarking, my personal advice is don't trust any benchmark you haven't forged yourself, because a benchmarking always really depends on the environment you're in. If you check across the Arango sites, of course, there are some benchmarks. There's actually an open source benchmark published by ArangoDB over the last years. And also other companies have other benchmarks here. So I would just urge you in terms of benchmarks, we can tell you now that ArangoDB has the best performance here, but you should actually really just benchmark that for your own use case on your own servers. Was there any other questions?
Yes, yeah. One other question in the chat. Will we provide the GitHub link and datasets at the end of the webinar? Yes.
Yes. I think I need to do the final commit. I only made the PR yet to my repo. But yes, this is all available in my demo repo along with all the other webinar examples. Any other questions? No, then I hope you enjoyed it. I hope you learned something about Games of Thrones. Thanks to you, I actually did. Thank you so much. I hope you learned something about graphs.
Yes, I did. I hope you learned something about Game of Thrones.
Yes, I certainly did so. And yeah, thank you so much for listening. We'll make all the data, links, and slides available probably either tonight or latest tomorrow. Thank you so much.
Thank you. Bye.